All right, we'll see how it goes. Okay, so we just kind of covered the higher heating value and lower heating value. Let's look at gas units. I'm usually pretty good about keeping these numbers in my head, but gas units it's just not in there anywhere. So let's walk through this thing and see what we can do. One part of the reason is they're kind of weird. You know, it's almost like you don't even want to remember it because you're just going to screw it up. So, well, it's not even the metric system. It's like it's the British. So here we are, one therm. Here's where it already gets weird. One therm equals 100,000 BTUs. And I think 1 BTU is the energy required to heat a pound of water 1 degree Fahrenheit. Does that sound right? Mm-hmm. Okay. So at least we kind of know what that is. So we're in pounds and degrees Fahrenheit. If you put 100,000 of them together, don't ask me why, it's not 10 or a million, but 10 to the 5th, BTU is one therm, equals, and then the rest is kind of straightforward. 29.3 kilowatt hours equals 105.5 megajoules equals. Now here's the important part. Equals approximately, like see that little wavy on there, 2.7 cubic meters of natural gas. All right. What's 2.7 cubic meters? Well, it's like a big refrigerator, or a small car, more or less. So, how much is that? Enough energy to power a human for a day? Well, not quite. Average human takes.
27 cubic meters or 1,000 BTU natural gas.
No, you're looking down below. It's right above that.
Oh, okay. All right. Yeah. Okay. Yeah. My bad.
Tell me where you're seeing that, though.
Gotcha.
Where are you seeing it?
That's fine. They converted it into something else. Right below it.
Oh yeah. Okay, we'll get there in a second. I'm just on this first little line.
My eyes dropped.
Okay. So really, if you're going to get all of your daily, your global recommended daily allowance of energy, you'd need 5.4 cubic meters of natural gas to kind of keep you going. Now, and then the other reason is this at exactly atmospheric pressure? No. It's got to have some pressure behind it, otherwise it'd never make it to your house. So that's kind of where this little approximate thing comes from.
So you're losing stuff.
Probably going to lose a little. I mean, and it's never going to be exact. I mean, there's a meter there that's counting it volumetrically, but it's not really taking into account pressure. So I don't know. Maybe you want to put a little
calibrator.
Well, no, forget that. Put a little pressure booster upstream of your own gas lines. You got to come in faster. I don't know. I always think it's a way to cheat the system. That's all. I don't know why. Anyway, that's to put that in context. So now, if we're looking at on down the road here, 1 cubic meter is 35 cubic feet. And I guess this is where the units start to work out pretty well, is to say that one I don't know why there's two M's here either. Because when I see two M's, I think mega. I think million, which would mean 10 to the 12. But it's not. 1 BTU equals 1 million BTUs. I'm going to skip the kilowatt hours and the gigajoules. I'll just say equals 27. There's your 27 cubic meters, Matt. Equals 1,000 cubic feet. So basically, if you look at this, you can say that so this is maybe a good way to convert it, because I think on your energy bill, you're probably going to see your gas in cubic feet or hundreds of cubic feet. So 1 cubic, not squared. 1 cubic foot. So this is actually something I should be able to remember. 1 cubic foot equals 1,000 BTUs, right? So with that 1 cubic foot of natural gas, you could take 10 pounds of water and raise it 100 degrees Fahrenheit.
Okay.
You know, you could go from about body temperature to boiling. You know, body temperature is about 100, boiling is about 200. So you should be able to take 10 pounds, you know, right around a gallon. So with that 1 cubic foot of natural gas, you should be able to boil a gallon of water. You know, that's probably a good way to think about it. Is that making sense? You know, if we're looking at so if it's a 1 BTU to take 1 pound through 1 degree, 1,000 BTUs would take 1 pound through 1,000 degrees, or 10 pounds through 100 degrees. So just, you know, you can kind of think in orders of magnitude there. So we're about a gallon to boiling. So now I'm going to remember from now on. Promise. And I expect you to too, right? Next time I say like, how many gallons of water can you burn with a cubic foot, or can you boil with a cubic foot of water? 10. 1 gallon. 10 pounds. 1 gallon ish. A gallon's 8 pounds, but whoever made that up. Okay, good. Now, global distribution. And these are the reserves. So again, we're back to our RP ratios, like reserves per production. Middle East wins or loses, depending on how you look at it. Kind of a mixed blessing to have all those goodies sitting under your soil, sand, as the case may be. They are not producing at a rate commensurate with their reserves. As you can see, North America, we are going gangbusters, 27%, beyond what our reserve rate is of about 5. Africa is about on par. The Soviet Union, or former Soviet Union states, they're a little lower than what their capacity would be. Africa, South America, pretty cooking along. Asia Pacific, producing a little unsustainably. So there's plenty of action still to be had in the Middle East. I guess that's the good news for some people. Oh, and you know, this whole stuff that's blown up in Ukraine is about natural gas too. I think, and I can't remember which way it's blowing, but it gets cold without that stuff. So people get grumpy when they're cold. Oh, because I mean, here's the issue. I mean, there's the pipelines. So one poor guy's downstream and some other guy with his hand on the valve. But how's it shipped? Well, this is liquid natural gas. So this is gas is compressed to the point that it's actually going through a phase transition from gas to liquid. It's going to be sitting at probably negative 170 Celsius to sit in that. But in terms of shipping it, better to spend the energy to compress it rather than
Pipeline under the ocean.
Pipeline under the ocean. Yeah. Whew. There's some bank.
That's pretty nifty, turn it into liquid and transport it.
Yeah.
Is there quite a bit of loss and all that?
Well, I don't know exactly what the numbers are for liquid natural gas, but I do know, for example, with our hydrogen fueling station, you're going to lose. Well, we did the numbers for coal. Like the transmission losses for coal were right around, are they 7? Can't believe. You guys remember that when we did the light bulb problem?
Oh, yeah.
Yeah. Well, it was 70% total, but it was, yeah, what was that one neat little problem we did? I thought it was sitting right there in chapter 3, conversion efficiency. Yeah, 7%. I'm looking at page 77. And I'm guessing it's going to be similar. You know, you might, running this tanker across the ocean, you might be sitting at 4 or 5%. You know, just imagine consuming a certain fraction of that to get there, and then the compression might be another 4 or 5%. So all told, it might be a 10% loss. But can't just leave it on the ground. Okay, now here are some onshore static tanks, stationary tanks. Also insulated. And there's one thing sitting here. It says this extra energy. So there's energy in compressing it. We just talked about, which gives it a higher CO2 emission factor than if you just kind of sent it through a pipeline. But there it is. But it says not sufficiently high enough to make it unattractive, say to burning coal, oil, what have you.
What's a few tons?
A ton here and there. Yeah, there's lots of air left. And I wish I knew my geopolitics a little bit better, but here's the arrow of flow for these Siberian gas fields. In fact, let's just look up where Ukraine is for a second. Then I'm going to stop my YouTube at 13 minutes. Ukraine news. Let's look at maps. Yeah, the Ukraine is downstream of the map we were just looking at. I mean, these guys are at the end of the pipeline, and so that's there's a lot of politics at play there. Okay, Ukraine's down here somewhere. What's that? Well, anyway, and then I'm gonna stop this YouTube and see how. Oh, man. I'll stop it right there.